let's look at how we can calculate the entropy change associated with a reaction. There are actually two different ways that we can approach this, and either one is a valid way to do that. So let me show you both of them. The first one, if we want to find the entropy change associated with a reaction at any given temperature, we can either use the absolute entropies, in which case we sum over the products times of n times the absolute entropies, and then we subtract off basically the same expression for the reactants, so the number of moles times the absolute entropy as a function of temperature. We can also do this sort of in the way we did with the enthalpies, where we look at the entropy of formation of each compound. So here we could instead sum for the product of n times the entropy of formation as a function of T, and subtract off the same thing for the reactants. If we are using this approach here, then we need to have the absolute entropies tabulated, and that often happens, although not always. But if you have the absolute entropies, this way can work out. We saw before that we don't always have the entropies of formation for the different compounds, so this approach can be a little bit more difficult because you might need to actually calculate those entropies of formation. And just as a reminder of how you would do that, if you had to, we integrate from T to 298, summing over all of the reactants, NCP over T dt, and then we have the entropy of compound formation at 298, and then the integral from 298 to T of the sum of the products, rather, NCP over T dt. So let's consider an example of the combustion reaction, again, of methane with oxygen, forming carbon dioxide and water vapor. And so we need some data for this, and so I'm going to give you both the absolute entropy and the entropy of formation, and both of these are going to have the units of joules per mole Kelvin. And I'm going to give you this for methane and for O2 and for CO2 and for H2O. So the absolute entropies, and we can sort of be checking that we have this right. They should be on the order of probably hundreds of joules per mole Kelvin, and all of the absolute entropies must be positive. So here are the absolute entropies, and then we can look at the entropies of formation. This one is 0 by definition. Okay, so we can then use either of the expressions from the previous slide, where either we are considering sort of the sum for the products of n times the absolute entropies, or the sum of the products times the entropies of formation, and then subtracting off the same for this. And it shouldn't make a difference because the entropy of the reaction is the entropy of the reaction no matter which way you do this. And in fact, if we calculate it in this way here, we find that delta S of the reaction is negative 5.3 joules per mole Kelvin. And if we calculate it in this way here, we find that delta S of the reaction is negative 5.233 joules per mole Kelvin. And while these numbers are not identical, I did take the values from different tables where you can see that sort of depending on how you were rounding the numbers, that you could come up in the end with the same thing. So the two approaches are equivalent, and that is how you can calculate the entropy change associated with a reaction.